Imagine asking a human software engineer to write a complex, multi-threaded database engine, but with one extreme constraint. They must type out the entire code base from start to finish in a single pass without ever hitting backspace, running the compiler, or testing the execution. It sounds absurd, because it is. Yet this is exactly how we traditionally use large language models. We feed in a prompt, and the model must generate the entire response in a single feed-forward pass of its neural network. There is no reflection, no debugging, and no self-correction. Loop engineering changes this fundamentally by turning static generation into a dynamic, repeating computational cycle. To understand loop engineering, we have to look at the three-part engine that drives it: the generator, the evaluator, and the feedback controller. Instead of a linear pipeline, these three entities form a closed-loop system. First, the generator model produces an initial output candidate. Second, the evaluator, which can be a secondary LLM, a deterministic unit test suite, or a runtime compiler, analyzes the output for logical errors, syntax flaws, or security vulnerabilities. Third, the feedback controller translates these errors into natural language or structured debugging trace data and feeds it back to the generator to trigger a refined iteration. Let us look at a simple execution loop in Python. We initialize a system where a generator attempts to write code to pass a specific unit test. If the test fails, we don't give up. We capture the traceback and feed it back to the model. The quantitative impact of this iterative looping is staggering. On benchmarks like Human Eval, which measures Python coding proficiency, a standard single-pass GPT 3.5 model might score around 48% accuracy on its first attempt. However, when embedded in a self-correcting execution loop with up to 5 iteration cycles, that same model's success rate climbs past 75% without updating a single weight in the underlying neural network. By substituting cheap compute at inference time for expensive training epochs, we unlock an entirely new frontier of capability. How does the evaluation stage actually judge output quality? There are three main approaches. First, we have code execution evaluators, where code is compiled in a secure sandbox, measuring actual output against expected test assertions. Second, we have LLM as a judge, where a separate, highly capable model inspects the output against a detailed rubric of style, tone, and logical consistency. Third, we have external APIs and tool verification, where the agent queries databases or calculators to verify mathematical or historical facts asserted in the generation step. But loop engineering is not a silver bullet. If not managed properly, loops can suffer from two fatal failure modes: infinite oscillation and degenerative decay. In an infinite oscillation, the generator repeatedly alternates between two incorrect states, for example, fixing a syntax error in step A, which introduces a logical error in step B, and then undoing that fix to return to the exact same syntax error in step C. In degenerative decay, the model's edits become progressively worse with each iteration as it loses track of the original system prompt, eventually devolving into hallucinations. To prevent infinite loops, engineers implement mathematically defined halting criteria. We define a state transition matrix and monitor the edit distance of successive generations. If the edit distance delta drops below a threshold epsilon, or if the iteration counter I exceeds a predefined maximum n, the loop terminates. Furthermore, we can use a reward function R of S to calculate the probability of improvement. If the expected reward of continuing the loop is less than the cost of token compute, we break early. Loop engineering represents a major shift in the historical evolution of AI. In 2020, we had zero-shot prompt engineering, where output quality depended entirely on the initial instructions. By 2022, chain-of-thought reasoning emerged, forcing models to write out their step-by-step thinking before returning a final answer. Today, we have moved into the era of fully autonomous agentic loops, characterized by frameworks like LangGraph, AutoGPT, and CrewAI, where models execute tools, evaluate results, and dynamically adjust their paths over hours of background runtime. The ultimate destination of loop engineering is self-evolution. When an AI agent can write its own code, generate its own tests, execute its own compilers, and use feedback loops to patch its own core logic, the boundary between software and model begins to dissolve. By structuring AI workflows as robust, self-correcting feedback systems rather than simple input-output functions, we transition from fragile conversational chatbots to resilient, autonomous engineering systems capable of solving complex, open-ended software problems on their own.